Good morning, everyone, and welcome to this webinar on GHG emissions and mitigation, which we will be discussing over the course of the next 2 hours. This webinar is part of a series on sustainable engineering that we are piloting and that will be part of a broader academy, combining a number of different topics, including the first one that we offered last month or so on fugitive dust mitigation. This is a series that's being offered through the California Local Technical Assistance Program, or CALTAP. And I am Tom O'Brien. I am the director of the CALTAP Long Beach and the Center for International Trade and Transportation. And our goal is to provide transportation-based training and education to local agencies, including rural agencies and tribal agencies across the state of California. CALTAP is one of 51 centers across the U.S. Funded through the Federal Highway Administration, OT. So there is one in each of the 50 states and Puerto Rico. And again, the goal of the LTAP program is to provide local technical assistance to local, rural, and tribal road agencies. We offer training that is developed through the federal government, some that is developed here in California. We are part of the Caltrans Local Assistance family based in the Division of Local Assistance, and we work with other partners across the state, including UC Berkeley and Sacramento State, to offer trainings on a variety of topics. We encourage you to stay connected with us by visiting our brand spanking new website at caltap.org. That's where you can find information on upcoming trainings, webinars, latest news and funding opportunities. It's also where you can sign up to get our regular e-blasts every 2 weeks, which will also provide information on the trainings that are available. And that includes the next in the series of this Sustainable Engineering Training Academy. We also offer a free equipment rental program that you can also get more information on through the website. We want to hear from you. We are in the business of highlighting local innovation. In fact, we help gather information on best practices that can be shared via the National Build a Better Mousetrap program. And so that's something else you want to learn more about. And so just subscribe to stay up to date with all that we do. Today's program, again, focusing on mitigation, is designed to provide you with an overview of construction-related GHG emission sources, consider the impact of the various phases of construction on the project carbon footprint, the effects of vehicle emissions and carbon sequestration, what approaches you can take to mitigate GHG, and how do you deploy them effectively within local government, and some of the alternatives that are available through things like biofuels and recycling to meet goals and mandates. Just a couple of housekeeping issues as we get started. Please mute your mics and webcams during the lecture. There will be an opportunity to share some of the stories that we asked you to think about in anticipation of this class. We'll do that at the first break. We do ask that you raise your hand to ask questions and then unmute yourself as needed. We really want this to be an engaging experience. We also ask that you introduce yourself in the chat box so everybody else can see the variety of of places that people are coming from and the expertise that they bring to the table. With that, I want to introduce our course instructor, who's Dr. Hamid. Our partner in the CALTAP Center, who is a professor in the College of Engineering here at Cal State Long Beach, and the director of the Center for Energy and Environmental Research and Services. So he is certainly the right person to be delivering this training today. It's an exciting webinar, and I'm going to turn it over to
Good morning, everybody. I think we lost Tom a little bit. Welcome, everybody. And Scott, I think that if you stop sharing the screen, thank you so much. Let me bring my screen up. Excellent. Let me just make it. Again, good morning, everybody. As Tom mentioned, my name is Hamid Rahai. I'm a professor of mechanical and aerospace engineering and also environmental engineering in the College of Engineering at Cal State Long Beach. I am the director of the Center for Energy and Environmental Research and Services at Cal State Long Beach in the College of Engineering. We have been in place for the last 20 years. Indeed, that the CEERS was established in 2003. And we have been a hub for research, innovation, technology transfer in energy and environment. We have about 8 or 9 awarded and pending patents in this area, over 100 publications, and we have had over $6 million grants and contracts over these years. We serve our community in this area, and also we serve our students. We have had over 50 some MS and PhD dissertation passed through our center in doing their research. The outline of the presentation is we start with a case study on pavement emissions, to be very specific. This is a case study from China, but I will differentiate this with respect to the projects that we do in the state. So you will see the differences, as we get to the interactive exercise where, I hope you had the Excel spreadsheet. It's a simple spreadsheet based on this case study, but it gives you an opportunity to try different scenario to see that how much would be the emissions if you do similar projects. Then we will have a Q&A, and hopefully we can interact and share experiences. Then we go over construction emissions and methods for carbon sequestrations, and followed by another Q&A. Then we have mitigation practices based on the guidelines from the US DOT, another Q&A, and then if we get time, hopefully we get time to go over the interactive exercise, the Excel spreadsheet that you have. Something that came up recently, it's the regulatory requirements, is that Congress has identified a national goal for environmental sustainability under 23 US Congress 150. DOT Rule 23 CFR Part 490 requires a state DOT and Metropolitan Planning Organization, MPOs, to establish declining CO2 targets for greenhouse gas emission measures. It does not mandate how target must be, but shows CO2 reductions over time. It also directs Federal Highway Administration to establish performance measures that the state DOT can use to assess the performance of the interstate and non-interstate national highway systems. Now, our presentation today is not directly associated with this, but it is actually indirectly associated with that, because it's related to environmental sustainability. And when we talk about environmental sustainability, we are looking at all activities, including construction activities, to reduce global greenhouse gas emissions for a sustainable environment. So let's talk about our case studies, pavement emissions. So This is a case study in China. The road specifications that you have is the length of the road is 20 kilometers or about 12.5 miles. The width is 8 lane, 92 feet. Depth, that's the depth of the road, is 28.35 inches or 72 centimeters. It has a hard shoulder width of 3.5 meter or 11.5 feet and a verge in the middle of the 0.75 meter or 2.5 feet. The components you can see here, there are 3 layers here of sub-base course, base course, and surface course, each one with corresponding thickness that is identified on the right-hand side. So what is the construction process? You look at the raw material production that include aggregate, asphalt, and Portland cement. Then we have a preparation of the material, which is including mixing phase, mixture transportation phase, laying down phase, and then we go to the installation that include laying down phase, compacting phase, and curing phase. For all of these activities, there are greenhouse gas productions that associated with the type of fuel that we use, type of electricity, type of activity that we do for this project. So it is something that we're going to discuss right after this. So the total materials that are used in tons for these projects that we have cement stabilized gravel subbase, that is the first layer. It had over 9,000 tons of cements, 180,000 tons of aggregate. Then cement stabilized aggregate base, it had over 16,000 tons of cements and 320,000 more than that of aggregates. And then the asphalt course that has 183,000 of tons of the aggregate, and then we had asphalt binder and mineral binder that comes on the top. So the production phase, based on the analysis done based on the type of fuel that it has been used. For aggregate in asphalt course, the energy that was used for producing this material was over 11 million megajoule, which if you convert this to the corresponding CO2 equivalent emission, carbon dioxide equivalent emissions is over 1 million kilogram. And then we have the cement stabilizer base, over 19 million megajoule, that corresponds to 1.8 million kilogram of the CO2 emissions. Aggregate in cement stabilizers, over 10 million megajoule of energy was used, and that is equivalent to over 1 million of CO2 equivalent. And then we have mineral powder in asphalts that give you the value for energy and CO2 equivalent. In total, for this part of the material, that for the asphalt and so on, over 4 million kilogram of CO2 equivalent was produced. That's the greenhouse gas produced. Now, remember that this project its example is from China. China uses a lot of coal in the preparation of the materials, and the emission here is corresponding, a big chunk of this emission correspond to the coal, burning of the coal fuel as a fuel. Then we have the greenhouse gas emission from cement productions that you can see here, is that the gravel subbase uses over 25,000 megajoule, corresponding 27 million kilogram of CO2 equivalent. And then we have a cement stabilized aggregate base that give you over $11 million kilogram of CO2 equivalent. I put a note on that on the bottom about that, how it has been calculated. A ton of cement consume about 97.4 kilowatt hour of electricity, 116 kilogram of coal, and 0.2 liter of diesel, which produces this much CO2, and then N2O, which is also 1.53 kilogram of N2O, which is a greenhouse gas, and also about 3.414 kilogram of the methane. Now, this doesn't seem to be that high, but the volume of the cement that has been used in this project is so significant, and that's why you see that you have so much CO2 equivalent produced. So, and then we are talking about the asphalt, production phase and installation phase, that you can see that. Again, the corresponding mass, that's the energy consumed and the CO2 equivalent produced for the top surface course, middle layers, seal coat, and so on. And then totally it come out to be over 2.79 million kilogram of CO2 equivalent that's produced. So if we look at the construction phase, including that the aggregate, for example, for aggregate is including mixing phase, transportation phase, laying down phase, compacting phase, curing phase. All of these, when it's added, it come out to be a total of 945,000 kilogram of the CO2 equivalent. And then we have also that the asphalt mixture, the asphalt mixing process, the mixing phase and transportation phase, laying down phase and compacting phase is not as significant as you can see as compared to the other activities. The amount of CO2 that's produced in terms of the kilogram of CO2 or CO2 equivalent, if you convert CH4 and N2O to CO2 equivalent, is not as significant. So if you look at total activities from asphalt, installation and laying down and compacting and everything, you see that the mixing phase is that combine everything together is over almost 5 million kilogram of CO2 emission. Transportation phase, about 123 kilogram of emissions. Laying down phase is 78, compacting phase, about 55,000. So altogether, over 5 million kilogram of CO2 emissions is produced. So if we combine everything and compare activities here for these projects, you can see that for CO2 from different activities, mineral powder is about 94,760 kilogram of the CO2 produced. Aggregate production and mixing all together from all phases of the asphalt, including the materials and so on, is almost 5 million kilogram of the CO2 emissions. And then transportation, 123,000, laying down 78,000, and compacting 55,000 kilograms. So the major component of the CO2 emissions for these projects comes from the aggregate productions and mixing for the asphalt constructions. When we go to cement, the significance is aggregate production is over almost 4 million kilogram of CO2 emissions, and cement production, which has been known that the source of greenhouse gas emission for a long time, is almost 40 million kilogram of the CO2 emissions. And then we have the aggregate mixing, about 231,000, transportation phase, 262,000, laying down phase, 395,000, compacting phase, 34,000, curing phase, 21,000. So the reason for this slide is that to show that the contributions of the production of the aggregates and the cement production to the total CO2 emission in these construction projects. And if I go back to the previous slides, you can see that in the case of the, again, asphalt productions, that again, the aggregate production for the asphalt and the mixing phase of this is contributes significantly to the CO2 emissions in this area, in these projects. So if you look at cement manufacturing, you can you can see why that we have so much CO2 emissions from the cement productions. You know that we start with the raw materials, then we have a crusher, transport, we have a raw meal, and then we have to heat this raw materials, and that's where we have a lot of energy per ton. It's a 3,150 megajoules of energy per ton of the cement that needs to be heated. And it produced about 479 kilogram per ton of CO2 in calcination process, and 319 kilogram per ton of CO2 from the fossil fuels used in this process. And then we have the cooler, cement mill, and then we have the logistic, which is the transportation and so on. And if you look at the total energy that is used for producing 1 ton of the cement, it's almost 4,000 megajoules, almost 4,000 megajoules. The corresponding CO2 that's produced for this 1 ton of cement is 925 kilogram of CO2. So, you know, when you compare the materials to materials per unit in terms of the energy used for production of the materials, you will see that a lot of time you see that the factor is not significant for cement. But please remember that for any construction projects, especially major construction projects like bridges, roads, and so on, we use a lot of cements. And that's why that it is significant to consider this, that how we produce cement, you know, that there is a lot of efforts at the Department of Energy and also EPA to try to transition the cement production to more less carbon intensive fuels. So in terms of the emissions of construction projects and total greenhouse gas emissions coming from this process is much less, because that is the major contributor to the greenhouse gas emissions in any construction projects. Now, you know, again, you know, we get materials internally throughout the US, and also we get materials from overseas. Yeah, and you will see that estimating how much greenhouse gas is produced from production of these materials become very difficult, because it depends on the source and where it has been produced. So with that said, that we will transition, as you will see, that we will discuss embodied energy later on, and as a factor that we can use to estimate, you know, that the energy used in producing this material, and that how much CO2 emission is produced from this as an estimate of that. And then I wanted to share this with you, this slides that talks about the contribution of the different industries to the global CO2 emissions. This is from data from 2017. And you can see that cement production is 7% of its share is 7% of the global CO2 emissions. If you compare with the gas and oil, it's 4%. Obviously, iron and steels are 8%. Building, transportation, power, agriculture contribute significantly. You can see the segmental of this. In terms of the dollar amount that kilogram of CO2 produced per dollar, you know, that is we get from this, is cement is the significant, because it's as compared to the others. You look at the chemicals is 0.3, iron and steel is 1.4, mining 0.4, oil and gas 0.8. You know that so it's a less, the other industries are less CO2 intensive as compared to the cement productions. So overall, you know, when we look at any kind of construction projects, we have to lay down that the process of the construction that include the materials that are used, the energy used to produce those materials, and those are related to embodied energy that we will discuss. And then the process of transporting and preparing these materials, to the construction site, and then the manufacturing or installation of this of the projects that at the site. So there are phases of the projects that we can lay down, and in terms of the material preparation, transport, and installations. And for each one, we can assess that how much greenhouse gas is produced for each phase. And then we can understand that how we can reduce greenhouse gas signature of these projects. With that said, that I am going to transition to Q&A here. And do you want me to stop sharing, Tom, before we?
No, you can, Hamid, you can keep the slide up. What we wanted to do here at this point in the presentation is pause for a little bit. Hamid's provided some really important context for the rest of the material that's going to follow, and I think lays out why this is an important topic to discuss. So we wanted to ask what questions you might have about information he's already shared, but we also want to hear from you why this is an important topic for you. Why are you interested in being part of this? And if there's anything you want to share from your own work experience, perhaps a related project that will give us that will help us shape the discussion during the rest of the presentation today. So maybe Scott and Hamid, you can just check the raised hands, and we'll proceed with this part of the presentation.
Scott, I don't see anything here. Do you see any raised hands or any questions?
Not so far. Does anybody have any questions or have anything they want to share? It's a good opportunity to kind of help us get to know you so that we can, like Tom said, help shape the discussion as we move forward.
Yeah, if nothing else, if you can let us know why you're interested in this topic, it helps us not only with this this topic, but others that might be part of the Sustainable Engineering Training Academy.
I see a raised hand. Taylor? Hi, Taylor.
Hello, thank you.
Nice
Thank you for
meeting
having
you.
this webinar. Yeah. I'm really excited to be learning a little bit more about greenhouse gas emissions in construction. I'm a grant writer for M&S engineers, and a lot of times we're trying to help our clients shape their project in a way that better suits the grant programs that we're applying for. Many of those have requirements for greenhouse gas reductions throughout the construction process. So from this, I was trying to learn just some like tips and tricks. I don't know, anything that we can like suggest to clients to help make their projects a little bit more sustainable, reduce their greenhouse gas emissions. Either different elements or specific to construction materials or processes that can be applicable to many different project types.
That's great, Taylor. Can you let us know when you're pursuing grants for clients? Do they tend to be federal, state? It might be helpful to the rest of the audience to understand who's funding programs in that perhaps connect to this area.
Mm-hmm. Yeah, it's mostly state and federal funding. Like we've done the Caltrans Clean California grant. That was the one that had a heavy emphasis on the greenhouse gas emissions. Also, the Urban Greening Program, I believe that was a state program. Trying to think of a federal one. I can't think of a federal one off the top of my head, but I know a lot of the California grant programs have a heavy emphasis on reducing greenhouse gases.
Yeah, that's great, helpful. Thank you very much.
Mm-hmm.
I see there are 3 other people. Allison, hi, Allison.
Hi there. My name is Allison Winter. I'm a grant manager with Interwest Consulting, and just wanted to echo what Taylor said about bringing that greenhouse gas emission reduction information to grants that we work on. We recently worked on a RAISE grant application, and that was a component that we really were able to help achieve. I think we got 8 out of 8 points for that grant. So it was highly,
Excellent.
we did talk about the use of low carbon concrete. I think that helped with the innovative element of the grant application. But yeah, I'm just really hearing more information about how we can quantify those, that information in the grants.
Excellent.
I'm really thrilled to see those of you who connect opportunities, funding opportunities to local government here, part of the discussion. It's really, it's good for us to know, and that you've learned about LTAP. That's pleases me even more. That's great.
Thank you. And I see Haley. Hi, Haley.
Hello. Yes, so to echo what Allison and Taylor had said, I am on the grant writing team here in the engineering department, and there is a huge push in state and federal grants for sustainability and mitigation practices. And then we also have our own, I'm with the city of Madera, and we have our own kind of sustainability standards for construction projects. And so I'm just looking to kind of gain some more information on ways that we can improve those standards going forward, since there is such a huge push on sustainability and mitigation practices.
Excellent. So as we continue, you will see that we will talk about recycling of the cements at the end, and the market for recycling of the cements that can be tapped in. And when we use recycling of the materials like cements, then we cut down on greenhouse gas production, because the material preparation portion of GHG is basically disappears, which is a major contributor to the greenhouse gas reductions. And you can see that you can assess the saving in or reduction in GHG if you use a lot of recycling materials. Stephanie.
Hi, good morning.
Good morning.
Can you hear me?
Yes, of course.
My name is Stephanie Oslick. I'm the West Coast Director for Environmental Services at Moffett Nichol. And Hannah, I work with Hannah Olson, who's also on the call. And we are working on helping our clients be more sustainable in their projects and trying to obtain Envision certification, basically to infuse more sustainability elements in their projects, both during design and construction. So always trying to look and hear more about latest and greatest, but ways that we can be a little bit lighter on the environment.
Excellent. Thank you so much. Thank you for sharing, Stephanie. Okay, anybody else? Any other question, comments, sharing experiences? I don't see any. Should we continue, Tom?
Yeah, let's continue. I'll just make one last pitch before you take over again, Hamid. A lot of the things that you're talking about, these approaches, these innovations, could very well be an appropriate submission for the Build a Better Mousetrap competition that we hold annually. And so I will once again encourage you to stay connected with CALTAP through our website, so you can learn more about those opportunities and hear about innovations from some of your peers and other local governments across the state. So with that, thank you. And Hamid, back to you.
Thank you so much. So let's continue. So let's look at the construction emission, an overall view of where the emissions come from and how can we reduce carbon through carbon sequestrations. So in general, when we talk about construction phases, we have demolition, site preparation, grading, trenching, building, paving, and architectural coding. And in general, when we talk about construction emissions, we have off-road equipment, on-road equipment, fugitive dust that, as Tom mentioned, we had actually a webinar on that last month. And then asphalt paving is corresponding to the example I just provided, and architectural coding. Architectural coding mostly related to construction at the end of the construction. We are not going to cover this in this webinar. We're not going to talk about architectural coding, but we will talk about off-road equipment and on-road equipment. So typical construction equipments, you can see here that dozer, excavators, we talk about bore and drill rigs and saw, obviously tractors, cranes, graders, forklifts, all of these, and rollers, bulldozers, compactors, mixer, scrapers, all of these are typical construction projects that we use, construction equipments that we use in any kind of construction projects. All of these, majority, almost 90% of these equipments use diesel fuel as the fuel of choice. But you know that in some cases we have CNG, in some cases we have LNG. You know, there are actually machineries that are nowadays that fueled by more or less intensive carbon fuels. So if those are the case, then we need to calculate CO2 equivalent. So greenhouse gases are rated against CO2 in terms of their global warming potential. CO2 has a global warming potential of 1. That is the reference. And then you can see that on the right-hand side is table of typical GHG gases. You know, that to be able to convert any other gases, GHG gases, to CO2 equivalent, we multiply the global warming potential of that gas by the volume of the gas or the mass of the gas that's used. So you can look at this, is that CO2 is 1, CH4 is 25. So methane you get mostly in agriculture and also from CNG and LNG fuels, you get that. You also get N2O in fuming, a lot of fuming, especially asphalt fuming in construction. You can see these gases. N2O is another one. It has a GWP of 298. The amount that is produced generally in construction are very small. It's not significant, as you saw from our example. But you know, the GWP factor is significant. So it becomes a factor, you know, when you calculate the CO2 equivalent of the total CO2 equivalent of the construction projects. And then we have the other gases, these like HFCs, PFCs, SF, NF, and other things. These are mostly you see in semiconductor industries. I put them up there that because when a lot of time we talk about constructions and manufacturing and so on, so sometimes these gases also considered significant that we need. As you can see, GWP of these gases are significant, is large. So in semiconductor industry, for example, when they do manufacturing of these, the amount produced is not that big, but because of these GWP factors, then the total becomes significant. But in construction, mostly we are concerned with CO2, CH4, and N2O, as you saw from the example that I presented. So let's look at a factor that's called embodied energy that we use to assess the contribution of the GHG from preparation of the materials. In general, when we talk about embodied energy, is the total energy associated with the production of a structure from mining and processing to manufacturing, transport, and installation. It is an estimate as the fuel and electricity sources used for all these processes could be different. It is very difficult to have an accurate account of the total energy associated with the production of the structure. As I mentioned, that when we look at the sources of the materials that are used in construction, you know, sometimes the material are produced using coal, as you saw in the example that I mentioned. Sometimes they are used, diesel fuel is used, and so on. And then in transportation, depends, mostly we use trucks for transportations and different kind of transport vehicles that they use diesel. But then if they are different, then we have to account for that. So it becomes very difficult to assess, in any construction projects, to calculate embodied energy from the beginning to the end. So instead of the embodied energy, we use processes energy requirement, or PAIR. It is the energy associated with the manufacturing of the materials. This is a PAIR is the one that used generally in calculating the greenhouse gas, in calculating the energy used for production of the materials. And then again, that once we know the sources of this energy, then we have the carbon equivalent or emission factor that we can use to see that what is the CO2 equivalent of these activities or this process. The greenhouse gas emission associated with PAIR depends on the type of fuel used and the duration of the process. If you look at the right-hand side, I have a list of the materials and the corresponding PAIR embodied energy in megajoule per kilogram. If you look at this list, you see aluminum, it has the highest, 170 megajoule per kilogram. Copper, 100 megajoule per kilogram. Cement, if you look at the cement, is 5.6. Again, you may say that within this listing, cement does not have much high embodied energy, but please remember that it's the total volume or mass of the cement that we use that is significant. And then obviously there is a lot of push to recycle aluminum. There is a lot of push to use recycled cements in any kind of construction projects. We also recycle copper and steel and other things. And as you can see, that recycling is a major thing in construction and overall in our society. So that give you an idea that in terms of energy saving, if you do recycling, if you use recycling, you can actually significantly reduce the amount of greenhouse gas production. So how do we reduce reduce greenhouse gas emission in any construction projects? Some of the practices for reducing embodied energy would be we use locally sourced materials to reduce transportation. Reuse and recycle materials from demolishing existing structures. That is very common, that if you can use this, or you tap into recycling markets that are available in the US, and I'll talk about it at the end of my presentation. Give preferences to materials manufactured using renewable energy source. And then we have the select low embodied energy materials, avoid wasteful material use, design for long life and adaptability using durable, low maintenance materials. Now, of all these bullets that you can see, the top are the ones that are significant. If we reduce the transportation, we reduce greenhouse gas emissions. If we reuse and recycle materials, whether from existing structure that is demolished or from the recycling market that's available, then again, that we reduce greenhouse gas emissions. If we use materials that are produced using renewable energy sources, we reduce greenhouse gas emissions. So these are the factors that you can use in any proposal or any projects to assess that, give actually a point to emphasize that because that the intention of this project is to use this percentage of recycling material, or we will use this locally sourced material here to reduce transportation, and we reduce greenhouse gas emissions. So let's talk about on-road vehicle emissions. So on-road vehicle emissions is mostly we get from transportation of the materials and processed materials, raw materials, transportation to the site. So when we want to calculate the emission from this, there is the vehicle miles traveled, how far we have to move the material to the site. And then there is an emission factor. I show you the list of the emission factor for the vehicles in a moment. So, if you multiply that by the type of fuel, emission factor depends on the type of fuel that we use. So if you multiply the emission factor by the VMT, vehicle miles traveled, you get the total emission, and that you get you can have from any of the vehicles that you use. So you can have multiple travel. You need to come up with the total vehicle miles traveled if you use one vehicle, or if you use 8 vehicles and one type delivery, then 8 times that the distance is the total VMT and times the corresponding emission factor. If you use different kind of vehicles with different kind of fuels and different kind of specifications, then the emission factor would be different. You have to calculate them individually and then sum them up to come up with the total emissions from on-road vehicles for your construction projects. Then you have the off-road equipments. It's a little bit more intense because we use a lot of off-road equipments to be able to do any kind of construction projects. So in general, this is the equation that has been used by CARB under the off-road 2011 methodology. Is emission is the summation of the emission factor times the number of vehicles involved, type of vehicle, the horsepower of that vehicle, and the load factor of that vehicle, and the activities. The activity is the hours of operations. And in general, emission factors is calculated by total daily exhaust divided by activity, by horsepower, by LF, and then there is the conversion factor that I have explained on the right-hand side, what those conversion factors are. Activities are hours per day. The default values are 8 hours per day for 5 days per week. So it's 40 hours operations. Horsepower is the average horsepower of the equipment. Load factor is the ratio of the actual output to the maximum output. It is dimensionless. The default value is taken from the database off-road 2011 from CARB. And then the 900,000 something is the conversion factor, tons to grams, to be able to convert this to the total ton of the emission. And then we have the index I is the number of pieces of equipment for each equipment type. So you may use, 5 tractors or loaders or, excavators or something like that of the same type. So for each set of equipments of the same type, we need to calculate the total emissions based on their specifications. And at the end, we sum them up, and that gives us the total emissions on daily basis, on monthly basis, weekly basis, or total for the projects for this, based on this summation, the total emissions are from every equipment that we have. So these are the typical emission factors that CARB has put out for off-road equipments. So you can see that this is for the year 2005. The bore drill rigs, depending on the horsepower, they are producing CO2, NOx, PM10, SOx, VOC. Here, so you can actually take these, how much it produce. You can take these values, as the emission factors that you can use that in any kind of analysis. Cements and mortar mixers, it's given to you. Cranes, industrial saw, crawler, crusher, and so on. And this is of highway trucks, other construction equipment, pavers, paving equipment, plate compactor, roller, and so on. And then again, other things for that you can see here. So there's a trencher, welders, and so on. So there are actually references available that people can input for their use to be able to calculate the total emissions for their equipments, off-road equipments. So we have atmospheric carbon. What are the sources of atmospheric carbon? CO2. There are two primary sources of natural and human activities. The natural source is primarily from animals that exhale CO2 as a waste product and methane or CH4 from fermentation in the rumen of cattle. The human activities obviously come from burning of fossil fuels. So from energy production that requires burning fossil fuels, or from transportation, from all activities that we have within the society that uses fossil fuels as a source of energy. So we talk about carbon sequestration. Is the process of capturing and storing atmospheric CO2. There are two types, geologic and biologic. Geologic is the process of storing carbon dioxide in underground geologic formation. The CO2 is generally pressurized until it becomes liquid, then is injected in the porous rocks formation in geologic basins. It is also used for for oil productions. This is process, it enhances oil recovery. The liquid CO2 is injected into the oil-bearing formation in order to reduce the viscosity of the oil and allow it to flow more easily to the oil well. Biologic is the process of storing CO2 in vegetation, soils, woody products, and aquatic environment. So this is the one that a lot we use in constructions. A lot of time we have to clear vegetations of in a land in preparing for a construction projects. So we have to assess that the carbon sequestration of the land before starting the construction projects, and then the carbon sequestration after the construction project is finished. So a lot of time after the first assessment, you know that at the end we need to actually plant trees. We plant a lot of trees after the construction project and come up with a way to show that either we'd have a net zero greenhouse gas emissions, or we have a saving in there. According to the Arbor Day Foundation, in 1 year, a mature tree, about 10 years from planting, will absorb about 48 pounds of CO2. Redwood trees have the highest CO2 absorption capacity. On average, it could absorb the equivalent CO2 of 2,700 vehicles annually. However, when it's cut down, it releases large amount of CO2. That's why a lot of time for redwood trees, you need to get permit to cut it down, and you have to have other mitigations, measures to show that instead of the plant this tree, as you cut it down, your intention is to plant trees to be able to recover, to reduce the greenhouse gas or recover the CO2 that was released into the atmosphere. Again, for biogenic sequestration, we use this formula to see that how much CO2 is sequestered. That it is equivalent to growing period of the plants or trees, the tree type, and the sequestration index. And so you can do it before and after, as I mentioned. If you look at a table here that in terms of the metric ton CO2 sequestered per year, based on the type of trees, You can look at the aspen tree, which is 0.0352 metric ton per year. Soft maples, 0.0433. Mixed hardwood is 0.0367. It's a hard maple, 0.0521. Then we have the others, juniper and cedar and Douglas fir and others that you can see. As you can see here, maple trees are the highest in terms of the metric ton CO2 that they can absorb per year. And this is significant. A lot of CO2 is absorbed into the trunk of the maple tree. It's not just the leaves. It's the trunk of the maple trees that absorb CO2. And so, a lot of time, if you want to consider the type of vegetation to plant, you can actually look at this table and look at this process and how to calculate, and you can justify to see that, that after, your design include planting this kind of trees. And for this kind of trees, the expectation is that we should be able to, recover release of the CO2 after the project is completed. And from this, we can show that there would be a lot of CO2 reductions. Now, the growing period is considered to be 20 years here. So it's important that, we estimate for 20 years, in 20 years, how much CO2 reduction we get for each tree that we are planting. And then we have you have seen recent projects, that is popping up. And actually, the Department of Energy has funding has funded projects in this area where there are huge fans that are placed, around certain areas that they actually suck in air, atmospheric air into this. And there is a scrubbing process, in the system that it actually absorbs CO2 and releases clean air to the atmosphere. CO2 is in the form of the liquid that is collected and then injected deep underground, as I mentioned. CO2 aid plant growth. There's a photosynthesis is the process by which plants use sunlight, water, and CO2 to produce oxygen and carbohydrates. Carbohydrates are the main source of food and energy for plants and also the basic building block of growth. So there are plants coming, it shows that in order to reduce the atmospheric CO2, there is a capturing of the CO2, atmospheric CO2, and through the scrubbing process, which is basically air washer with some chemicals, you produce a liquid that has CO2 content, and then you inject it deep underground, and it actually it's useful in plant growth. The things that I should mention here, this process of running huge fans is if the electricity comes from renewable energy, then obviously this is effective. If the electricity or the energy used is coming from fossil fuels, then obviously that's not effective. So we all know that in order to be able to sequester carbon using this process, we really need to use renewable energy. Any projects, as I mentioned, that if you are clearing a land that had vegetations before you start your projects, or a road or bridges or anything that you have, you need to assess the difference between before and after of how much carbon is reduced. So assessing carbon sequestration before you start the projects, and then carbon sequestration after you finish the projects. So your proposal is actually needs to include this process that after the project is done, how you mitigate the carbon sequestration that was there before you start the projects. So it is, it's a summation, as I said, that, what's the area, how much CO2 sequestered before that, and after the projects and before the project, and you get the difference. If the difference is zero, then that you have net zero gain. And then if the difference is negative, you actually have advantage for this this process. On the left-hand side in the table, I put an estimate of the metric ton CO2 per acre of the land that you can use for coming up to see that before you start or after you if you do trees or shrub or anything, you can see that how much CO2 sequestered before and after. So for forest land, for shrub is 14.3 metric ton CO2 per acre. For trees is 111 metric ton per acre. These are estimates. Remember that that we can do individual calculation based on the information that I presented just now, in terms of the type of trees and the number of trees and the estimated life of the trees and so on. But that if you just want to have a rough estimate, you can use these numbers. Cropland, 6.2 metric ton CO2. Grassland, 4.31 metric ton CO2, and obviously wetland doesn't have much, and so on. So with that said, an overview of the construction, activities and emission from construction activities. I want to pause here for any Q&A, or if you want to share any data or information with everybody, with the participants, before we talk about mitigations. Scott?
Excellent, Hamid. I have no questions.
Excellent. Anybody has any question?
I know there's a lot of data being shared here. This is probably very useful as a after training resource. So what I'll do is make sure that everybody's got a copy of the presentation, and we'll send that out afterwards.
Excellent. Any question? I guess, should we continue on mitigations?
Looks like we're ready to go.
Excellent. Okay, so let's talk about mitigations. These guidelines for mitigation come from US EPA in 2009 on the documents from potential for reducing greenhouse gas emission in the construction sectors. US EPA reviewed the construction activities in the US, and the directions and recommendation that you see is based on the overall activities in the US. Before we go there, about talking about mitigation, I need to go back and talk a little bit more about PEAR, or embodied energy, that we discussed, in terms of the megajoule of the energy used per unit production of the materials. Remember, those are for the US. This data that I mentioned is US. It's different than what we have presented as an example or case studies from China. As I mentioned, China uses a lot of coals. In the US, we don't use as much coal. So the data is the baseline data that is used to estimate how much energy is used for unit production of the materials. And then we look at to see what is the sources of this energy and how we can calculate CO2 emission in the US. All right, so let's look at mitigations. Based on the overall, review of construction in the US, the most influence in producing greenhouse gas emission from a construction project are fuel selections, equipment idling, electricity use, equipment maintenance, equipment selection, material recycling. Some influence possible: material selections, material shipment, employee commuting, vegetation removal. We just talked about this a little bit. Little influence: site selection, structural design, and performance. Okay, so let's talk about these operations or these processes. Fuel. When we talk about fuel, mostly we use diesel fuel in constructions. So far, for diesel fuel, 1 pound of CO2 per unit material produced 22.37 pounds of CO2 per gallon. So diesel fuel produces, for each gallon used, we get over 22 pounds of CO2. If we use highly efficient equipment to be able to reduce the fuel consumption by 3% on annual basis, we reduce more than 2 million metric ton of CO2 emission in the US based on the overall average construction. If we use 10% less fuels, then that goes up to 6.73 million metric ton CO2 reduction. For gasoline, it is 19.5 pounds CO2 per gallon. Again, 3% reduction in fuel reduces 0.63 million metric ton CO2 reduction. And if we go with 10%, it's over 2 million metric ton of CO2 reductions. Propane, a lot of forklifts use propane. And so it produces 12.66 pounds of CO2 equivalent per gallon. And so we don't have estimate of 3% reduction and so on. And natural gas is the lowest, so 11.7 pounds CO2 per 1,000 cubic feet used. If you reduce the consumption by 3%, you can see that we save 0.36 million metric ton of CO2 emissions. We reduce that. And then if you go by 10% less fuel consumption, we get almost 1.2 million metric ton CO2 reductions. Now, one of the major things in natural gas is NOx. So NOx is the greenhouse gas, or N2O, I should say, N2O as a component of the NOx, that greenhouse gas. And you saw also the global emission gas factors for the N2O, that's very high. So if you multiply the the volume by the GHG factor, you get the equivalent CO2 equivalent. There are methods that have been used to reduce the NOx emission from natural gas. Exhaust gas recirculation is one. So there are equipment that have the newer engine from Cummins that has exhaust gas recirculations in there, 15% about that actually get the NOx production to very low levels. So those equipments that use natural gas with the new version of the engines, the updated engines that has exhaust gas reduction recirculations, then have much less greenhouse gas emissions. There is also engines that use humid air systems that we have put out and we have patented that cut down by greenhouse gas by over 60%. This is for natural gas, and we also tested that our system on diesel engine. You know that diesel engine Also, it produces a lot of NOx or N2O as component of the greenhouse gas. And if you use humid air system that on diesel engine, you also cut down by greenhouse gas production by 60%. Idling. A Class 8 diesel engine at high idle consumes 1.2 gallons of the diesel per hour, resulting in 26 pounds of CO2 per hour. At low idle, it consumes 0.6 gallons per hour, equivalent to 12.8 pounds CO2 emitted per hour. A 2005 study of construction equipment in California shows on average heavy-duty diesel trucks idle over 29% of their operations time. So another study indicates reducing idling by 10% results in over 500 pounds of CO2 emission annually. So reducing idling reduces fuel consumption and obviously provides a significant saving, at the same time reduces greenhouse gas emissions. So another factor in reducing greenhouse gas emission in construction is to reduce idling. One thing I have to mention that a lot of Class 8 diesel engines, when you turn it on, especially in the cold environment, it's hard. If you turn it off, then it's hard to turn it on back on. It's the process and so on. But that's why they keep it running all the time. So I'll talk about in a moment about the biofuel and so on. And you see that in that case, there is actually a way of reducing greenhouse gas emissions. Equipment maintenance, improperly inflated tires and poor wheel alignment reduce the fuel efficiency of the heavy trucks by 3 to 4%. Improperly maintaining equipment increases greenhouse gas emission. So if you look at a forklift, improperly maintained propane-powered forklift could emit more than 2.3 tons of CO2 per year. So maintenance is another thing that we need to maintain construction equipment to make sure that we can control the amount of greenhouse gas emitted during the constructions. Okay, biofuels. The emission factors for Bio 100, that means that 100% biofuel is zero. So we have 0 CO2 per gallon. If we switch to 3% biodiesel, we again save over 2 million metric tons of CO2. If you switch to 10% biodiesel, again, you save CO2 emission. You reduce CO2 emission by 6.73 million metric tons of this. B20 is the one that has been used. It's a 20% biodiesel and 80% regular diesel. The emission pound CO2 per gallon is 17.8. It's much less than 100% diesel. And if you use, and you don't have to really change the equipment, I mean, the engine. The engine can handle B20 without any modifications. Generally, most of the engines, used in construction, they can do that. If you use B20, if you save 3%, switching to 3% and so on, you can see that how much CO2 reduction you get, in terms of the switching to the biodiesel or B20. Recycling. Recycling is a major component of major process for reducing greenhouse gas emissions. In 2003, US EPA estimated approximately 170 million tons of building-related construction and demolition materials were generated in the US. Of these materials, 48% were recovered, and the rest were transferred to landfill. So recovering and reuse those materials would reduce greenhouse gas emission as well as reducing landfills. So it's important. Recycling is a major way of reducing greenhouse gas emissions. So here is the secondary market for construction and demolition materials. We talk about the reuse of demolished structures on site, but sometimes, we don't have a structure on site, or the structure that we have on site does not produce enough materials in terms of the recycling materials. So here is generally for concrete, there is a recycling market. For activities like building construction, building demolitions, infrastructure demolitions, recycled market for road base is 68%. Especially is substituted for virgin aggregate. For new asphalt hot mixer, 9%, general field 7%, other 7%, aggregate for concrete mix, 6%. So basically for road base, we use a lot of recycling materials. And this way you can actually reduce emissions. If you go back to the examples that I presented, you will see that because of the production and mixing of the aggregates, there is a lot of greenhouse gas emission produced during that process. If we can use recycled material, that is a saving for us. So, and it can be used. Asphalt pavement. Aggregate for new asphalt hot mix, 66% come from recycled materials, and there is a virgin as a substitute for virgin aggregates. Sub-base for paved roads, 33%. For building, the construction, recovering lumber, remilled into the flooring. We didn't have data for that, so I didn't put anything in here for the building construction and other things. But in general, the most that are used are for road base. Aggregate is the one that you can use recycled materials, and that is where the greenhouse gas emission savings are. Okay, so again, on the recycling and reuse of construction material, emission factor for recycled material for steel is 1.79 metric ton CO2. So these are the saving. Recovery rate, 97.5%. Quantity of material recycled annually, 40 million tons. CO2 equivalent emission avoided through recycling is over 71 million ton of CO2 emissions equivalent. So you can see that for materials like asphalt is over 4 million, for concrete is over 1 million CO2 equivalent from recycling. Obviously carpet and other things are, that you use in constructions is different. They are not as much as steel and other things. So recycling is a major way of reducing greenhouse gas emissions. So basically, to go back, to the initial slides on ways to really reduce greenhouse gas emissions. It is the type of fuel that you use, and equipment idling. If you can reduce equipment idling, you can reduce greenhouse gas emission. The type of electricity used, is it from renewable energy, or is it from a plant with coal or anything? So electricity usage, reduction of electricity usage, and the source of electricity are major factors here. Equipment maintenance, save you fuel and save and reduce greenhouse gas emissions. Equipment selections, type of equipment that you select is that. Material recycling is a major component of reducing greenhouse gas emissions. Material selections has some effect. Material shipments, the process of shipping material has some impact. So if we can have locally sourced material, locally sourced supplier, then obviously we reduce the transportation. So the vehicle miles traveled, so we reduce emissions. Employee commuting, and that if employees are on the site, obviously we reduce traffic and we reduce greenhouse gas emission, but it's not that significant. A lot of time we have projects at very different sites in the US, and it's far and different locations that require some commuting. So obviously that has some influence, but it's not significant. Vegetation removal has some significance, as you saw that. So it is, these are the factors that we can use in reducing greenhouse gas emissions. So with that said, that is conclude my presentation before we go to interactive exercises. Any question? Scott?
There's a lot of great information shared here. If there's a question that you came or something that you came to this this class wanting to know, and maybe Dr. Rahai didn't cover it, ask that as well. He's an expert in this field, and it may be something that he just hadn't touched on yet. So if there's any questions you have, since we have a little bit of time, particularly even related to some of the topics that got mentioned, we encourage you to check in and see if Dr. Rahai maybe has a good answer for you.
Hi, hey everybody. This is Ken Taylor with Griffith Company.
Hi, Ken.
I appreciate the information that's being shared, and it is a lot. I think in a previous presentation, we were going through some of the mitigations that we're using for our equipment, and there are some Tier 4 requirements that we're trying to meet with our fleet, which helps in emissions reduction. So, I mean, I know you presented some percentages there. Is that due to just the reduction in fuel burning, or is that in the actual, tier setup for the equipment?
When it comes to, thank you for the question, Ken. When it comes to greenhouse gas emissions, we look at the operations, and in transportation, that we use different kind of equipments, different type of vehicles. The question is that what type of fuels are used, how much fuels are used, and that is depending on the vehicle miles traveled. So for that specific vehicle, you can say that, that I'm going to use this vehicle, and it's a diesel fuel, and it has these emission factors, and we're going to have this much vehicles, this much miles traveled. And so we multiply, we get an estimate of the emissions. The larger the vehicle, the higher the amount of fuel that's used. Obviously, the higher the emission that come with that. Now, if I switch to, biodiesel 20%, that I can cut down, the emission by 3% or 10%, depends on how you, manage the saving and so on. So it is relative to the size of the vehicle, the type of vehicle, the amount of fuel that's used, and the distance that's traveled. And the class, when they say class this, the emission factor is related to the class of the vehicle. So if you use the right emission factor, you get a good estimate.
Thank you. Yeah, that makes a lot of sense. I'm currently on a project. It's a very large project out in Barstow for BNSF, and there's been an estimate on the number of hours, for equipment to be running and so forth. And they've been basing it on the size of the equipment, just like you mentioned. and the hours that it's going to be running, whether it's daily to make sure we're not exceeding the maximum daily loads, I guess, and then just overall. So it's interesting because the models that they're running are also accounting for the trains that are coming through the site, and then also the because the project is so large, we're even accounting for the operators and so forth that are going to be commuting to the site, you know, and parking and then working and stuff. It's a very complicated model. I don't know that much about it. I just know that it takes several weeks for them to even run the model itself.
Yeah, as I mentioned, you know, that if you go back to this one, you know, the overall assessment of a project from Department of Transportation is you can see that, you know, commuting is, you know, employee commuting is a factor. Now,
Yes, sir.
How
Mhm.
much that is a factor as compared to the overall emissions, the total emission that you get from the project, that is, you know, that's something that you may assess to see that how much it is, you know, if cutting down. I mean, there are, I can tell you that, you know, there was one case study I was reviewing for a city in California that they were actually transporting. It was an agricultural projects, it wasn't a construction projects, but they were transporting people from different site and to the agricultural site and for the activities. They came up with an estimate of how much CO2 emission they get from this transportation. Then they assess to see, okay, how much it costs them if they house people at the site, you know, or in the vicinity, in the near city, you know, at the site, how much it costs them and how much CO2 saving they get. Based on that assessment, they offered this housing, you know, temporary housing to the people who were working on the site to live very close to the projects. This not only they improve safety, they cut down on potential for any kind of accident or anything, but they also cut down on CO2 emissions.
Mhm.
And in terms of the cost, it was kind of, you know, they had fuel saving costs related to that. They had, because they actually rented, you know, buses to move people on daily basis from the site, you know, collect them and then deliver, come to the site. Because of there's cost associated with that. So they had saving in that. And when they calculated that in terms of the cost, it was a kind of net zero. And then, so the net was zero. But then they had significant improvement in terms of the reducing greenhouse gas emissions and also in terms of safety, because there has been accidents and also include fatalities, you know, during this process at different sites, at different, you know, location in the US. So this is one example I read, you know, I remember that.
No, that's very good. I appreciate that. And I don't mean to hog up the conversation here, but no, I agree with you. I think the camps that they can put on site, that helps with the commuting, and it all really adds up, like you say, and you can actually save time, save fuel, and I like the safety aspect of it too. So
Yes. Yes.
appreciate your response, and
thank you so much, Ken. Thank you
You're
for
welcome.
coming. Thank you.
You're welcome, sir.
Any other question? Okay, so I don't see any other question. So I'm gonna stop sharing and move to the exercise. I don't know if Scott, did you email everybody the?
Yes, everybody got a copy.
Okay. So this is a not very sophisticated Excel spreadsheet that we developed quickly for these presentations. Let me see, everybody. Let me just close this. I don't know if everybody see my Excel spreadsheet.
We can. You might,
Excellent.
you could probably expand a little bit to, or zoom a little bit.
Okay, so let me see if I can. Is this better?
Yeah, that's great.
Excellent. So this is basically based on the case studies. So we put in everything according to the case studies. The only thing is different is that the emission factors that you can see here, we included the global warming potential of CO2 and embodied energy according to the data from the US DOT and also the US construction industry. So it's in terms of the CO2 equivalent that is produced, it's it's based on activities in the US. So and if you look at this, that we also put in information about the equipment, paver, cement, mixer, crawler, other things, and how much CO2 and how much greenhouse gas emission they produce, and then corresponding CO2 equivalent in there. In terms of travel, and, traveling to the site, it's again based on the case studies, based on the capacity of the truck. We put the number of yards that is being transported, and then we use the total material to estimate the number of trips, because that case study that I mentioned, they don't provide information on the number of trips. So it's an estimate, I should say that. It's an estimate. Also, we have information about the manufacturing of the materials and how much megajoule of energy and the corresponding kilogram CO2 is produced. You can see that. So let's look at the input. First of all, the length was 12.45 miles, as you can see here with the width and shoulder. These are the specifications that you can change. The road makeup for the base and the cement and the asphalt are, that we assume cement is 5%, gravel is 95%, or cement 20%, gravel 80%. And then we have aggregate. For the asphalt production, we have binder 13%, aggregate 80%, and mineral powder 6.5%. All of these can be changed. You can change that. And then the estimate of the metric ton greenhouse gas emission produced based on the emission factor that we put in different tabs, and the embodied energy that you have seen there is given and is highlighted in red, that you can see that. So there is a equivalent for manufacturing, there is equivalent for travel, and there is equivalent for installation, and then summation of those two give you the total greenhouse gas emission. So if I change the length to 20 miles, you can see that this data on the right-hand side table changes quickly. If I send the transport distance from manufacturing to site to 20 miles, again, those change. So you can change those things to come up with this. Now, in terms of the emission coefficients, and let's see if I can get to the travel. We talk about the use of different kind of fuels, the type. Now, we haven't really put in all the information there. So this spreadsheet, even though if it's very simple, it's 80% complete. But our plan is to actually include biodiesel and both B100 and B20 here, that you have this choice of selecting those to see how much emission reduction you get from these, all of these things. And again, here you get this option. So once we have those in there, there are some variation you can play around with in terms of the distance for travel, in terms of the amount of the raw materials used, in terms of the size of the road, in terms length, width, and so on, to get an estimate of greenhouse gas reduction. Again, this is a very simple a spreadsheet based on the example I provided. Our work continues to really make it as comprehensive as possible, this one. So to take into account other elements that I mentioned in terms of recycling, that if you, change the percentage of the material to recycled material, how much saving you get. This spreadsheet doesn't have really, it doesn't take into account for the employee participation, employee travel, and other things like this. It doesn't take into account that. But that gives you a way of playing around with the numbers to see for your own projects, for any of your own project, to see that if what is the baseline for these pavement projects, and if you're using this, then you can actually use this for on-site projects if there is no traveling involved. So for the road size, you can put the area of the length, width, and shoulder. You can put the area, an estimate of the area of the size, and then the rest of the stuff can be changed. But this is for pavement, basically. We designed this for pavement. So I just wanted to share this with you as a way to do some interactive exercises and practices, and wanted to see that if anybody has any questions. Any questions, any inputs? Anybody want to share anything? Apparently not.
I'll go again.
Oh, Ken, please.
Yeah, you estimate the kind of the movement, the mileage or whatever of the equipment,
Right.
moving dirt around and stuff. We've been getting pretty specific with the big Barstow job, and I want you to take a look at it once we get it kind of dialed in, if you wouldn't mind. It'd be good.
Oh, absolutely, absolutely. That would be interesting for me too. Thank you so much.
Yeah, we've been doing some they do a model of the Earth movement. As we're moving a big site. It's almost, well, I think they reduced it. It's 26 million cubic yards of material that will be moving around, and we are going to balance the site, so there won't be any haul off or anything like that. But I mean, we're looking at 2 years of, I guess, these 657 machines, those big scrapers,
Oh, huge.
Yeah, the big ones that for almost 2 years, 60 of them for almost 2 years to move that kind of dirt. And that's why the modeling that they're doing is so significant. And they've developed these models where, we're going to move dirt from here to here for a while, and then we're going to move dirt from here to here for a while. And so really the mileage that these scrapers are doing are pretty significant. And so they've asked us to look at a couple different options too to reduce emissions with conveyor systems that can be run with electric motors versus diesel and stuff like that. So there's a couple innovations and options that we're looking at. So
do you use any alternative fuels, or is all or diesel?
They've been asking about some of the electric equipment. It's just not quite as powerful, efficient. But we are using a lot of the biodiesels and things of that nature.
Excellent.
Which really does help, like you're mentioning. So, but I think the conveyor system is attractive to a degree. The only issue there is you got to kind of double handle the material, and they really don't like touching material twice. So, because that adds up to time and equipment and stuff like that. So they have to really kind of analyze and balance that out.
So what we found out, as you mentioned, Ken, is that for any project, there are two things. One is that the emission factor reductions, but then the duration of the operation and cost with the manpower and equipment maintenance and other things. Those are also need to be taken into account. I'm sure that they do and everything. That then the total emission reduction per unit cost come out. And so for any operation, there is a factor that you can look at is that, okay, so for 1 ton kilogram of CO2 equivalent reduction per cost, if I switch to this operation is how much, if I switch to that operation is how much, and then that is compared. And that's a way to really present different cases, and in terms of the budgetary issues and the cost of the project is something that, you know, people look at.
Right. No, absolutely. Even a 25-cent increase in cost over 26 million cubic yards, that adds up pretty fast.
Oh, so much. So the cost per metric ton of the CO2 reduction is, you know, is something that people look at. I mentioned it in the slides that I had at the end of first part.
Yep.
That when you talk about the cement productions, you know, the cost for the cement per metric ton CO2 was really high, you know. So a kind of similar approach is used when you look at the total cost of the projects and reductions when you switch from technology, fuel, operation, and so on. But in construction, you know, in your case, you're not using any kind of recycled materials. So, you know, that the major contributor to greenhouse gas emissions would be from operation of the equipment, and also, you know, mostly operation and type of fuels are used, and the duration of the projects, as you mentioned. So then it come back to that, okay, so if the duration is increased or the number of hours that the unit is increased, how much saving in greenhouse gas emission we get, and how much increase in cost do we get, you know, for the projects. And then it come back that CO2 ton CO2 emission saving per unit cost, you know, how much it costs to save at 1,000 ton or a ton of CO2 equivalent for different type of approaches. And that's how you can compare.
Yep. Thank you very much.
Thank you so much for your question, Ken.
Yep, no problem.
Appreciate that. And I'm interested in that project, really. If you can share with me whatever you can share, that would be interesting.
I'll see if I can get some permission to do that.
Excellent. Thank you. Any other question, comments, inputs? Anybody has any input about this presentation? Anything that I can add to for the next one that it can kind of improve the presentation or improve the content? Any comment? You can put it in the chat if you don't want to talk.
Well, and Hamid will be blessing everyone with a little after session email survey to
Excellent.
capture some ideas or some thoughts and what they'd like to see for next time.
Oh, excellent. So then we can rely on that. I have let's see, in the chat. Okay, so thank you so much, Taylor. I saw in the chat you put a note. Take care of yourself and happy holidays to you.
Hamid, thanks so much for your time today and for sharing this research with us.
Thank you so much. Thank you, everybody.
As Tom mentioned at the start, this is the second of a number of sustainable engineering trainings that Dr. Rahai is going to be releasing over the course of next year. We've got a couple of different venues, channels to be able to let you know about that. Subscribing to our e-blast is kind of the most important one, then you can be kept up to date. If you're not familiar with, and I hope that you all are, with our website, we maintain a training catalog here, which is a collection of all of the trainings that are promoted through local assistance, a lot of which are either engineering based or compliance based. One of our strong mandates is to support Caltrans Division of Local Assistance in helping local agencies to maximize their access and efficiency in working with state and federally funded programs, which are managed through Caltrans. We've got Sherry Graham, I think, is in our audience too. Sherry keeps us up to date through the Caltrans Division of Local Assistance blog, and we encourage you to subscribe to that as well. Between ours, you'll be inundated with all the available training and stuff that's coming up. Sherry, did you want to say hi?
Hi, everyone. My name is Sherry Graham. I'm with Caltrans Division of Local Assistance, and Caltrans subsidizes these trainings for local public agencies, as Scott mentioned, with the LTAP Center. So he's sharing the blog right now. We highly recommend, if you go to this blog, I'll drop the link in the chat field. On the right side column, you can enter your contact information. You'll subscribe to where it says on the far right, DLA email announcements. You can subscribe to receive our weekly DLA announcements and our specific office bulletins that'll go out. You'll also find out more news about upcoming trainings that we provide that are subsidized, right, for local public agencies and tribes. And then also any upcoming news from Federal Highway Administration or state policies or anything related to your local project. We highly recommend go to the blog, sign up to receive the weekly emails. At any time, you can unsubscribe from those emails as well. I'd also like to drop in the chat in just a moment. You can also contact Division of Local Assistance directly with any specific questions. You can reach us at caltrans.dla@dot.ca.gov. It's our general inbox, and we can answer your questions. If we don't have the answer, we'll get it for you. And then we also have a new engagement form on our homepage, and I'll go ahead and drop that in the chat as well. Thanks, Scott. I'm glad everyone has enjoyed this. Hamid, this is great information.
Thank you so much, Sherry. Thank you for your comments and all the support. I appreciate that.
Thank you, everyone, for coming, and we appreciate your spending your morning with us.